Hello, good morning everyone. I am V. Surya, Assistant Professor, Adiman College of Engineering and Technology, Department of ECE. I am going to go do a video lecture on electromagnetic fields. Uh, Electromagnetic force is nothing but a Lorentz force. It is given by physics scientist Henrik Anton Lorentz. The equation of Lorentz force is F is equal to Q into E plus U cross B. The Lorentz force equation is quite useful in determining the paths charged particles will take as they move through electric and magnetic field. If you also know the particle mass m, the force is related to acceleration by the equation F is equal to ma. The first term in the Lorentz equation represents the electric force Fe acting on a charge q with an electric field is given by Fe is equal to Qe. The electric force is in the direction of electric field. Magnetic force. The second term in the Lorentz force equation represents magnetic force Fm of n on a moving charge q is given by Fm is equal to q into u cross b, where u is the velocity of the charge in meter per second within a field of magnetic flux density b. The units are confirmed by using the equivalences Weber is equal to volt into second and Joule is equal to Newton into meter, that is equal to Coulomb into volt. The magnetic force is at right angle to magnetic field. The magnetic force requires that the charged particle is to be in motion. It should be noted that since the magnetic force acts in a direction normal to the particle velocity, the acceleration is normal to the velocity and the magnitude of the velocity vector is unaffected. Since the magnetic force is at right angle to magnetic field, the work done by the magnetic field is given by the formula W is equal to integral over force into the differential length. Here it will become force into dl cos 90 degree. So since cos 90 is 0, it will be equal to 0. Magnetic force on a current element. Consider a line conducting current in the presence of a magnetic field. We wish to find the resulting force on line. We can look at a small differential segment dq of a charge moving with a velocity u, and we can calculate the differential force on this charge by using the equation df is equal to dq into u cross b. The velocity can be written as u is equal to dl by dt. By substituting the velocity equation, df is equal to dq into dl by dt into b. Now, since dq by dt is in coulomb per second corresponds to the current I in the line, we have df is equal to I into dl cross b. We can use this to find the force from a collection of current element using an integral. So, the total force in the current element is given as F12 is equal to integral over I2 dl2 into B1. Magnetic force of infinite current element. Let us consider a line of current I in the AZ direction on Z axis. For current element IDL, we have IDL is equal to IDL into AZ, where AZ is the unit vector in the direction of Z axis. The force is given as dF is equal to IDL in cross B, where B is the magnetic flux density for an infinite line of current. The magnetic flux density H is given as I by 2 pi rho, whereas the magnetic field intensity B is equal to mu naught into H1. We can represent B is equal to mu naught I by 2 pi rho into A phi. We know this element produces magnetic field, but the field cannot exert magnetic force on the element producing it. As an analogy, consider that the electric field of a point charge can exert no electric force on itself. What about the field from a second current element IDLB on this line? From Biot-Savart law, we see that the cross product in this particular case will be 0, since IDL and AR will be in the same direction. So we can say that a straight line of current exerts no magnetic force on itself. Magnetic force of two current element. Now let us consider a second line of current parallel to first. The force dF12 from the magnetic field of line 1 acting on a differential section of line 2 is dF12 is equal to I2 into dL2 cross B1. The magnetic flux density B1 for an infinite length of current is recalled from equation B1 is equal to mu naught I1 by 2 pi rho into A phi. From that we can say rho is equal to y and A phi is equal to minus of Ax. That's just opposite to the direction of x axis. Inserting this in the above equation and considering that dL2 is equal to dz into As, the big equation of force becomes F12 is equal to mu naught I1 I2 divided by 2 pi y of minus Ay integral over dz. To find the total force on a length L of line 2 from the field of line 1, we must integrate dF from plus L to 0. We are integrating in this direction to account for the direction of the current. We will get F12 is equal to mu naught I1 I2 into L 2 pi y into Ay. This gives us a repulsive force. Here F1, F21, the magnetic force acting on line 1 from field of line 2, we would have found that will be the negative of F12. So F21 will be equal to minus of F12. From this we can conclude that two parallel lines with current in opposite direction experiences a force of repulsion. For a pair of parallel lines with current in same direction, a force of attraction would result. Magnetic, in this more general case where the two lines are not parallel or not straight, we could use the Biot-Savart law to find the magnetic flux density. The equation is given as below.